Session started. And our first speaker will be Aron Wall. Okay, Aron.
All right, so I'd like to talk about give an overview of what we now know about the thermodynamics of black holes and other horizons. I was asked to give originally to talk about progress in area-entropy relations, and that would also have been a good title of this talk. The outline of my talk is I'm going to try to say a bunch of true statements until I run out of time. But we're going to start with the static case. Most of this section is actually going to review some older material that may be familiar to the experts in the audience, but not everybody in the audience is an expert, and I'm hoping that if there are grad students here, they'll get something out of this. So here's the Penrose diagram of an eternal static black hole. I've chosen to draw ADS Schwarzschild. There's asymptotically ADS boundary conditions because this is strings, but you could have other kinds of boundary conditions here, and most of what I have to say would still be true except for anything that's related to ADS CFT. So what's true about this space-time? We have a future horizon and a past horizon, and they meet at what's called the bifurcation surface. And because of the killing symmetry of the space-time, it has constant area along the horizon. So the space-time has multiple killing vectors, but there's one that's the most important one is the one that's called the horizon-generating killing vector, which is null. Oh, this got messed up here. I don't know what happened here, but this is supposed to look like a nice boost here. So it'll go like that and like that. The horizon killing vector takes the horizon to itself, so it's null on the horizon. And though it looks like a time translation at infinity, it looks like a Lorentz boost near B. So if we actually take this killing vector to be normalized with respect to some notion of boundary time, if this were asymptotically flat, it would be obvious what the right normalization to use is. Here, we have to sort of pick an arbitrary convention of normalization because there's a redshift factor as we go out to infinity. But with respect to this normalization, with respect to some boundary clock time, the surface gravity, which is defined as the absolute value of this boost quantity along the horizon, is actually constant along h, which is called the zeroth law. It's related to the fact that black holes have constant temperature when they're in thermal equilibrium. So the key ideas of this subject, in order to have nice thermodynamics, you want an energy, a temperature, and an entropy. The energy we already have in general relativity of a black hole. It's just the ADM mass, which is measurable out at infinity from the gravitational field. The temperature is proportional to the surface gravity that I just described. And if you use the first law, which is really the Clausius relation, not energy conservation, as it's sometimes defined as the first law in thermodynamics treatments, you can work out from that the entropy is given at leading order by the area of the horizon. And then there's some quantum and stringy corrections that I will describe later. So this is the first law. If the black hole is rotating or charged, you actually need some extra terms related to the angular momentum or to the charge. But morally, this is the statement. Now, if we do quantum field theory on this space-time, then there's a very special state that is called the Hartle-Hawking State, and that is the one that is generated by a Euclidean path integral. This slide looks a little, I thought this was okay when I went through it, but I obviously didn't check carefully enough. Possibly we should switch to the PDF, but is that something you could do? I'm sorry. There we go. Okay, so the special state, this is the Hartle-Hawking state, is defined by taking your Lorentzian path integral, and there's some boundary condition out at infinity here. We Wick rotate this to Euclidean signature, put the same boundary, or the Wick rotation of that, same boundary condition here, and then this path integral, which is now a Euclidean path integral, specifying the values of the fields on this slice, is the special state. That's the Hartle-Hawking state, which you can think of as a wave function over the values of the fields. I've chosen to put a scalar field here, but you could put whatever kinds of fields are in your quantum field theory. It's defined by this Euclidean path integral. Now, I've also drawn the both sides of the Lorentzian path integral here, because once you have this state, you can evolve it either to the future or to the past. These are just sections of the complexified manifold. So because if we now complete this by looking at both sides of the Euclidean path integral, since we started with a space-time that has a killing symmetry that looks like a boost here, the Wick rotation of that is a rotation. And so this space-time is rotationally symmetric. And the fact that it's rotationally symmetric means that you can choose to think of the path integral instead in radial coordinates as taking you around a circle. And when you go around a circle in Euclidean path integral, you have something periodic. On one slice of this, you actually define a density matrix. It has both a bra and a ket because you have both sides of this path integral. And when you do so, the density matrix ends up being a thermal state with respect to its modular Hamiltonian K is in this case the boost energy that's just associated with the generator of this translation. If we go back to the Lorentzian signature diagram, then this tells you that this region, the region that's in the domain of dependence of this slice here, is in a thermal state with respect to the boost killing energy that pushes this slice forwards. So that is one fundamental property of the Hartle-Hawking state, is that it's thermal in this region. And that's related to the fact that if we're doing ADS-CFT, then we can instead think of a CFT path integral as being at the boundary here. And when you do the CFT path integral, we get what's called the thermofield double state, which is an entangled state of the two CFTs. But if you restrict it to just the left CFT or just the right CFT, then you get a thermal state. And the entropy of one of these CFTs in the ADS-CFT dictionary is related to the entropy of this black hole, which at leading order is the same as the area of the horizon. This might make you think, since we have a thermal state over here that's entangled with a thermal state on the other side, and the same thing happens with the CFT here, it might make you guess that these left and right wedges of these diagrams are dual to the left and right CFTs respectively. And this turns out to be not only correct, but part of a bigger statement that is going to hold in dynamical situations that is called entanglement wedge reconstruction. That's a statement in more general spacetimes of what these CFTs are actually dual to geometrically. Back to statements which are true independently of holography, and therefore can be justified even if these boundary conditions are different. Another way we can analyze the Hartle-Hawking state is by instead choosing to look at the future horizon. And if we include all of the future horizon, including the part that's behind the past horizon here, we get a codimension 1 manifold sitting in the bigger space-time that actually has more symmetry. For example, it has a null translation symmetry that pushes you up here, which is not actually a killing vector of the whole space-time. It's just a killing symmetry of this submanifold. And it turns out you can show that the Hartle-Hawking state on this slice, so it looks, if you have reflecting boundary conditions here, this looks like a Cauchy slice in the sense that it gets all of the information, but actually whether or not, even if this were asymptotically flat and some information could escape, it's still true that if you restrict the Hartle-Hawking state to just the future horizon here, it is a pure state, and in fact it is the ground state with respect to null translations on the horizon, as was shown in several foundational papers on this subject. Actually, though, a stronger statement is true. The Hartle-Hawking state is actually the ground state with respect to the null energy that is integrated along any individual light ray of the horizon. So here since this is a Penrose diagram, each of the points in this Penrose diagram represents a whole sphere. So for example, this B here is the bifurcation surface, is an entire slice of this cylindrical horizon. And these are the light rays that make it up, the things that are traveling at the speed of light. So for each of these light rays, if V is a null coordinate, then I have, that is affine, meaning that it's uniform under parallel transport, then the quantum field theory stress tensor of the Hartle-Hawking state exactly satisfies that the renormalized stress tensor integrated along this is 0. So the fact that it's a null translation symmetry means that this would be true integrated over all of these light rays, but it turns out these light rays aren't competing with each other. There's no frustration in a light-like direction, and so it can actually be the ground state of each of these individually. There's no frustration, there's no competition to minimize things along these different light rays. I've actually written this not just as an expectation value statement, but actually as an eigenvalue statement, because that is a stronger statement that is true. When we say it's the ground state, that means that this is actually the lowest bound for all states. So any state would satisfy the average null energy condition that says the integral of TVV along this light ray is non-negative. And so it's actually easy to prove the expectation value of this statement using Lorentz symmetry. This is the only finite quantity that this could be under the killing symmetry. But if you also know the average null energy condition, then you can make a stronger statement that this holds without any quantum fluctuations. So because the energy is 0 in the vacuum, it can't be the case that quantum fluctuations make it sometimes negative and sometimes positive if being negative is forbidden. So furthermore, because this average null energy integral, by the ANE, the average null energy, I mean all of this except the greater than or equals 0 part, I mean the left-hand side of this inequality. Because that quantity generates null translations, it turns out that the Hartle-Hawking state therefore has a thermality property, not just in the wedge that's outside the bifurcation surface, where you can write the quantity K, the modular Hamiltonian with respect to which it's thermal, as just the killing flux, which is TVV times an additional factor of V dV, integrated over these y directions, of which there's d minus 2. So it's not just true, this thermality statement is not just true above the bifurcation surface. It's also true if we push this up to a non-bifurcation slice, which may even be wiggly. And if we take the region above here and we integrate the modular Hamiltonian along this region, it still has a local formula. There's just some extra function here that tells you where this slice is. It's the sort of the null translated version of this formula. I should mention that if we had asymptotically flat boundary conditions, this would be true up to a constant related to stuff going off to infinity that is not a function of where this slice is. I've done my best to try to show this with two different diagrams here. This is my attempt to indicate that the surface here, this green surface, is wiggly in the dimensions that I've suppressed, so that this wedge region is also a little bit wiggly in these directions. I don't know what you think of my art here, but this is the best I could do. This property of general thermality turned out to be what you needed in what I needed in my dissertation work to prove that the second law also holds in quantum semi-classical settings, which is called the generalized second law. So a lot of this is review of older stuff. Let me now say what's new about this in the last few years. The main thing that is new about everything I told you is that the statements I told you are now pretty much shown to continue to hold in general interacting QFTs, although some of the works I'm mentioning here may require the existence of a UV fixed point. For example, it's remarkable that although we actually had proofs of the average null energy condition for free field theory for a long time, for the interacting case, it's actually only in 2016 that we got good proofs of the average null energy condition. And there are two different ones, one of which involves the monotonicity of this quantity called the relative entropy. That's sort of like a free energy difference between the state compared to the vacuum. Delta means you're comparing to another state, which in this case is the Minkowski vacuum. This proof works by taking a wedge region here, and you use the fact that the relative entropy is monotonic, where it monotonically decreases when you restrict from A to B, and also when you restrict to B prime and A, and the entropy terms end up canceling out, and you get the average null energy condition if you're also good enough to calculate the modular Hamiltonian when you null translate using CFT techniques, which these people did. There's also a recent argument involving the causality constraints that is applied to the light cone OPE, where you take two operators as they approach the light-like separation, like this and like this, and in that limit, you can argue that the dominant term looks like an average null energy integral. And if you throw in a bunch of other things, including stuff related to the chaos bound and some rules and various other things, you end up with a positivity constraint. The other statement I made, that there's this thermality property on non-bifurcation slices. This was shown by Cassini, Teste, and Torriba, who derived the formula for the modular Hamiltonian on null slices, and in a follow-up paper by the same authors, they actually used it to prove a version of the A theorem, which is a monotonicity of RG flow in 4 space-time dimensions from entanglement entropy, similar to the Cassini and Huerta C theorem in 2 dimensions. Now, for full disclosure, these papers were all written describing the case of Minkowski space. I believe that the essence of their proof will probably be extends to killing horizons without much trouble, but for some reason they didn't want to make these stronger claims. But I believe one can probably rely on these stuff all being true for killing horizons as well. And one thing to note, just to not give a false impression, is that the average null energy condition in curved space-time is actually, if we're away from a killing horizon, it is actually not true in general. The average null energy condition is actually only required along complete null geodesics to have the additional property of being achronal, which means that no two of their points are related by time-like curves. In Minkowski space, all null geodesics period are achronal, but in a gravitational field, this is no longer true. And if you have a massive object like a star and a light ray going through it, in general, if I start far enough to the left and I end up far enough to the right, I can go faster than this light ray simply by going a little farther away from the star, which by Pythagoras, I don't pay very much price for going farther away from the star, but then I don't get slowed down by the star's gravitational field as much. So there's a nice paper by Graham and Olam where they showed that actually what you want to do is impose the achronal average null energy condition, which generically actually implies that no achronal complete null geodesics exist. But amazingly, pretty much all the general relativity proofs that we wanted to prove from the average null energy condition that required some energy condition that we might be hoping to hold in quantum field theory, the fact that there are no achronal null geodesics is actually sufficient to prove most of the things you wanted the average null energy condition for in the first place. So it holds trivially. Generically, it holds trivially, but the fact that it holds trivially is itself very non-trivial and tells you a lot. So that was a review of some things that happen with static black hole thermodynamics. If you have a stationary horizon like a Kerr horizon, most of what I said goes through the same, although there's some more difficulties in defining Hartle-Hawking states. But I want to focus now on the dynamical case where things are changing with time. One bit of a preliminary concept that's important to have here is the notion of expansion. So if I have a codimension 2 surface sitting in my space-time, I can shoot out light rays in one of the 4 null directions from that. So let's say I shoot light rays in the outward null direction, for example. Then those light rays define a codimension 1 surface. There's a codimension 2 area of slices of that. And so what you can define in an infinitesimal delta A interval or region of this, you can define the rate of change of the infinitesimal area element logarithmically in the null direction. This is called the expansion theta. And in the special case where the outgoing light rays satisfy that the expansion, which I've drawn in the v direction here, is 0, then, and usually we also want to impose the condition that the ingoing light rays are doing as we expect and shrinking an area. You would normally expect, in that case, special case, we call this a marginally trapped surface. You would normally expect, of course, that the outgoing light rays from a surface will be typically expanding somewhere, but in a region of strong gravitation, this is not necessarily the case because space-time is curved, and the existence of these trapped surfaces play an important role in the Penrose singularity theorem, who used this together with the null energy condition and a causality assumption to prove the existence of singularities. Here, we're going to be using it to analyze different types of horizons in the black hole. So I showed you earlier the Penrose diagram of the eternal black hole, but a more interesting case is to consider spacetimes in which we add various sorts of matter. Now, I'm not actually showing the matter in these spacetimes, But if we start with the eternal black hole and just drop in some matter fluxes in various directions, you can show that what you expect to have happen is that it extends the Penrose diagram to be wider than it is tall. So this becomes a long wormhole, which instead of having a light ray that crosses, this is marginally, just barely not traversable. In this case, the wormhole is much more non-traversable in the sense that there's a bigger gap here. So in that case, there are a variety of special surfaces that you may want to consider to ask about their thermodynamic properties of them. One of the most interesting ones recently is called the extremal surface. This is also the HRT, Hubei-Rangamani-Takanagi surface. This is the special surface where both of the thetas, theta v and theta u, are both equal to 0. And so the first order variations of this area are 0, so it's stationary or extremal. This is the surface that people use to calculate the holographic entropy of the CFT. It's a special case of a more general result that's usually stated when you have regions of the CFT, but in this case I'm focusing on black hole horizons, and in that case this thing doesn't touch the boundary, it's just a compact surface lodged in this throat. You can still define event horizons as the boundary of the past of infinity, but now the past and future event horizons on this side do not coincide with the past and future event horizons on this side. There's also what's called trapping horizons, which are surfaces, codimension 1 surfaces that are defined, they have codimension 2 leaves that have the property that one of these thetas is 0. So for example, for this theta, we have for this surface, we have the property that the theta v going in this direction has stationary area. And so actually, this is a highly non-unique concept in general, except when you have spherical symmetry and you impose that T also has spherical symmetry. There are actually many trapping horizons, also called holographic screens, or dynamical horizons, depending on who you talk to, that have this property. But we can make statements that are true about all of them. Here's a different Penrose diagram where we form the black hole from collapse from the matter I haven't shown. In this case, the horizons might look something like this. So at late times, when the black hole settles down and becomes stationary, these two concepts of horizons coincide, but at earlier times, this is generally not the case. I've also shown here a general null surface, just in a random place, to say we may also be interested in identifying laws of thermodynamics that would not require us to be at some sort of horizon, but that might just be true anywhere. So classically, if we assume the null energy condition, then the following statements are generically true, as are their time reversals. And I've only put the word generically into this sentence because a lot of these things are inequalities, and non-generically, you can also have things be equal or coinciding. So you can figure out what happens non-generically from these statements. But generically, the trapped surfaces always lie inside of event horizons, as shown in the picture. Another statement we can make is that both the H plus and the T plus type definitions of horizons have an area that is monotonically increasing. So the fact that this area is monotonically increasing as we go up is the Hocking area increase theorem. Sean Hayward showed that in various circumstances you have an area increase theorem for these trapping horizons. And now this trapping horizon is defined so that the null direction, the area is stationary, but the trapping horizon need not itself be null. Generically, it can be space-like or it can be time-like. Sean Hayward showed that the area will be monotonically increasing either along the space-like pieces or the time-like pieces. Recently, Raphael Busso and Netta Engelhardt showed that if these things are glued, whenever these things are glued together on a mixed signature surface that's partly space-like and partly time-like, this monotonicity of area still holds in a uniform direction, which is actually in the space-like outward direction or the time-like pastward direction. The time-like pastward direction is a strange thing for a second law to hold going backwards in time, but maybe it makes a bit more sense if you think of it as related to the fact that this looks like going forwards in time at the boundary here. So these are two versions of what's called the second law of black hole thermodynamics, that if we interpret the area as some sort of entropy, it means that the entropy increases. Other statements we can make: the extremal surface actually has less area than this surface, here where the two horizons intersect, and the area of the extremal surface is also gives us the leading order in 1 over n entropy of each of these dual CFTs, as conjectured by HRT and proven by a path integral argument by Lukowitz and Maldacena. So there's a question, in some sense there's an embarrassment of riches here. We of course have many surfaces in this space-time that have areas, and we might wonder what is their interpretation. It makes sense, since information is preserved on the CFT, that the fine-grained entropy of the CFT would be conserved with the CFT at time, so it makes sense that it would correspond to just the codimension 2 surface that is in the space-time, so that that's preserved. These other areas would then represent some sort of coarse-grained entropy that mixes some of the degrees of freedom of the CFT. In case this terminology fine-grained and coarse-grained is not familiar, here's a lightning-fast review of how the ordinary second law of thermodynamics works. We normally assume we have some sort of special initial conditions, and as time passes, we go to a state that has where the molecules in this box of gas are more spread out, and we say that there's a higher entropy state. As a first pass of defining the entropy, we can look at something like the von Neumann entropy. Is something that we would expect to be bigger for a state that has more possible room for these in the phase space for these molecules to move around in. But of course, the fine-grained entropy is actually conserved under unitary time translation. Another way to say this is if we started with a very special state here, and time evolved by unitary evolution, this state may look typical, but really it's an equally special state because it has the property that 10 minutes ago, or whenever this was, all of the molecules were back in one corner. So to say that this state has higher entropy than this state, to allow the entropy to increase in statistical mechanics, you need something that is called coarse graining, which is some way to forget the detailed correlations of the molecules. In other words, there must be some way to identify a coarse-grained procedure for calculating entropy, such that the coarse-grained entropy is actually higher than the true fine-grained entropy if you had access to all of the observables. So we could say this area increase suggests that there's some way of understanding this as a coarse-grained entropy. So far, while this was originally proposed to work for the causal horizon, we only have a good story along these lines for the trapping horizon, not for the causal horizon. So this is some work I did with Netta Engelhardt, where there's a quantity called the outer entropy, where if you have a marginally trapped surface, then you can hold fixed all of the field data outside, space-like outside that surface, and then vary the data inside, and you can ask, what's the biggest value of the fine-grained entropy, that is the surface X, that's compatible with that? For a wide class of these marginally trapped surfaces, you can show that this actually is equal to the area of the marginally trapped surface itself, which means that its area can be interpreted as a coarse-grained entropy in the Janesian sense of maximizing an entropy subject to certain constraints, where here the constraints are the field data outside. So we showed this by constructing an explicit solution where we constructed the extremal surface by gluing a stationary null surface to the marginally trapped surface. These surfaces have the same intrinsic geometry and therefore the same area. And then we showed you can't do better than this. And this gives a statistical explanation for the area law, at least in the case where T plus is space-like, because there you can show that as you move in a space-like outward direction, then you're maximizing an entropy subject to fewer and fewer constraints on the data, and therefore that entropy can only go up. We do not know how to understand in statistical terms the second law in these other cases where T plus is time-like or on the causal horizon. I would say those are still open questions. We also discussed what the CFT boundary dual of this is, but I don't have time to go into that. The next topic I'd like to mention is quantum corrections to the story that I just told. So for that, we need the concept of entanglement entropy. So here we have a Cauchy slice shown in the space-time, and we can define a codimension 2 surface, and for this story, we want the codimension 2 surface to have the property that divides the Cauchy slice into 2 regions that we can arbitrarily label the interior and the exterior. There's quantum matter, there's quantum field theory state that divides between these 2 sides. And formally, we define the entanglement entropy as just the von Neumann entropy on one side or the other. If the state is a pure state, so that this is really just due to entanglement between the 2 sides, it actually doesn't matter which of the 2 sides you use because the entropies are equal to each other in that case. If we had originally started with a mixed state of the whole Cauchy slice, it would actually matter which side we would pick, and then we just need to pick a side. The entanglement entropy, however, has a problem, which is that it's UV divergent, coming from field modes that are very close to E in the short distances. Fortunately, the divergences are local, and that means that you can keep them under control. For example, the leading order divergence scales with the area of E. Because the divergences are local, you can play a game that is similar to renormalization in quantum field theory. In the case of a gravitational theory, what we do is we define an entropy that is finite that is called the generalized entropy. So we start with a suitably quantum version of the Bekenstein-Hocking entropy formula. Then we write down the outer entropy. Sorry, not outer entropy, outside entropy. This is not the same as the outer entropy I mentioned with the work in Netta. This is just the entropy the entanglement entropy outside. And what we do is, although this thing is divergent, because the divergences are local, they can be absorbed into counterterms. So the leading order counterterm looks like the area and can therefore be thought of as a shift in the value of 1 over g, depending on your UV cutoff scale. And this is, in fact, the same renormalization of 1 over g that you would see if you did a standard Feynman diagram treatment, assuming that you use the same regulator that you use to regulate the entropy. There are other sub-leading counterterms that would be related to higher curvature terms, integrals of other things that, for example, in 4 dimensions, this would be a quadratic divergence that gets absorbed here, but there'd also be some logarithmic divergences that get absorbed into more complicated but still local terms. This suggests a way to extend classical GR proofs and ideas to semi-classical situations involving quantum fields, which is we take the area, which is the leading order piece of it, and we replace it with this entire quantity, the generalized entropy. In that case, we had this notion of expansion. This is the same as the formula I gave you for the classical expansion, just written slightly differently. We can define a quantum expansion by just substituting in the generalized entropy here. And then if we take a suitable limit as we push forward the codimension 2 surface on a small infinitesimal area element, we can define a generalized entropy variation that's called the quantum expansion. A recent very strong result, a conjecture that is called the quantum focusing conjecture, is that a second derivative of the generalized entropy, so if I take another functional derivative of theta, we conjectured that this would be negative. This is analogous to the fact that light rays focus in classical general relativity if you have the null energy condition. And by taking a suitable limit where Newton's constant goes to 0, and you're doing a quantum perturbation around a surface which is classically stationary, this thing becomes there's a contact term where y and y prime are evaluated at the same point, and this becomes actually a statement about ordinary quantum field theory. It tells you that the stress energy tensor, its expectation value is bounded by a certain local second derivative. I mean, the derivatives are local at the same point of the von Neumann entropy all the way to the outside of the surface. Although there's a number of limited proofs of this earlier, well, fairly broad, some of them. The general proof has only come in 2018 of this quantum null energy condition. And surprisingly, it's actually saturated in the case of CFTs that are interacting in higher than 2 dimensions. So this is a statement that's true on general null surfaces, and using it and other quantum information principles, one can actually show that pretty much all of the story I told you earlier about the second law continues to hold if you make suitable substitutions. By suitable substitutions, I mean that we're now going to define the quantum extremal surface as extremizing the generalized entropy, so that it's the capital theta that's 0, and similarly a quantum trapping horizon should be one that where one of these thetas is 0. Then all of the quantum versions of the previous statement still hold. The quantum extremal and trapping surfaces fall behind the event horizon. And there's now generalized second laws where both H plus and the quantum trap surface plus have increasing area monotonically. It's also, I don't know if anyone has actually shown the analog of my statement 4, but it should be true. And finally, the generalized entropy should give the entropy of the dual CFT, but in this case, the statement has now been shown by a path integral argument to all orders in 1 over n, which is the same as h bar in the bulk. At the first subleading quantum order in h bar, if we're expanding our state around a single space-time background, that means the following relationship holds. The CFT entropy, as shown by Faulkner, Lukowitz, and Maldacena, is just the same as the generalized entropy as x. I did not write the quantum extremal surface here because at this order it doesn't actually matter which of the two you use, because there's no first order area change as you vary away from an extremal surface by definition. So this was derived by a path integral. But if you then linearize around any state rho, you can actually also derive a statement for the modular Hamiltonian of the state rho, which is minus the logarithm of that density matrix, viewed as an operator. And so for any state rho, you get an operator equation relating the modular Hamiltonian of the CFT to the modular Hamiltonian of the bulk. And this could be acting at, you then take the expectation value in some other state. This gives an enormous amount of additional information about ADS-CFT and shows ways forwards for reconstructing information behind the horizon. It also, as shown by Jaffers, Lukowitz, Maldacena, and Su, implies that the relative entropies, this free energy-like quantity, also agree between the CFT and the bulk. This, in turn, implies the property that's called entanglement wedge reconstruction, which is the more general statement I promised you earlier, that if we find the extremal surface here, and we look at the two CFTs here on the long wormhole, then it's the case that the right CFT is dual to all of the data in this wedge region, and the left CFT is dual to all of the data in this region, where these time-like regions are the only parts that you need both CFTs to reconstruct. Similar statements hold in the case of holographic entanglement situations and asymptotically ADS, but for simplicity, I've chosen to discuss everything in the black hole case here. It's also possible to generalize the coarse graining setup I just mentioned to quantum extremal surfaces using the work of Kahan and Faulkner that I mentioned. This was done recently by Busso, Chandrasekaran, and Shahbazi Moghadam at Berkeley. I want to briefly mention the progress that's been made on stringy and higher curvature corrections over the past several years. If you remember the formula for the generalized entropy that has these counterterms here, in this case, there's a good story about what these counterterms look like. If you using the fact that the action and the entropy, there's techniques for deriving the entropy from the action of your theory. So if you start with your action that may be a function of curvature, and in general this happens in string theory, it also happens with quantum loop corrections. If you're doing GR, you might try to keep these higher curvature terms out, but at some order in the Planck or string length they'll come in, and you take this action, you can derive an entropy functional. For a long time, all we actually knew was what the entropy functional should look like for stationary black holes. And this term is called the walled entropy. It agrees with the Bekenstein-Hocking entropy for GR, but it's more general in general theories. Recently, we now know that there are what the corrections look like in stationary cases, at least to quadratic order in the extrinsic curvature, which is good enough for the simplest corrections to the Einstein-Hilbert action. So there are a bunch of people who worked on this, largely by doing things like, for example, Shidong generalized the path integral derivation of Ryu-Takeyanagi to higher curvature gravity theories and showed that these kinds of terms involving the extrinsic curvature of the codimension 2 surface appear. I do want to briefly mention that there's an alternative perspective on these higher curvature terms that is in some work that I did, where you could start with an arbitrary, let's say, metric scalar field theory of gravitation with an arbitrarily complicated, not complex as opposed to real, action. And if you do linearized perturbations of the gravitational fields around the Killing horizon, then it turns out you can always construct an entropy density that focuses. So you just write the analog of the Einstein equation with the VV components. I claim there's always some S that this is the second derivative of. And the basic technique for getting this S is you just classify all quantities in this theory according to their boost weight, the weight under a Killing transformation. So HVV has boost weight of 2 because it has 2 V's in it. V's count positively, U's would count negatively if they were in the expression. And so schematically, you can always write this quantity as a sum over background terms times variation terms. And on a Killing background, Because of the killing symmetry, anything that has positive weight vanishes. So this is always negative. This term is always positive. And in fact, it has at least 2 plus nv derivatives. And by repeatedly differentiating by parts, because this one can only absorb n, you always end up with at least 2 v derivatives outside the expression. And it turns out for f of Riemann actions, this actually agrees with the entropy formula you get from other derivations. So this is actually, I'm out of time. This is actually my last slide. I just wanted to say that we could ask the question, what is the meaning of all this generalized entropy we're discussing? For a static horizon, it's very plausible it counts the degrees of freedom if we understood quantum gravity at the Planck and string scale. For example, there's this picture that Susskind and Uglum came up with that they argued the Bekenstein-Hocking entropy comes mainly from strings crossing the horizon, but I don't know if anyone's really made their picture satisfactory because to get the A over 4 term requires understanding off-shell string theory. People have proposed that this generalized entropy might just count the quantum gravity entropy of a general region, but I think because the CFT entropy is constant, this is probably only true of the holographic entropy surface, and we need a story related to coarse graining to understand what the meaning of the area of other surfaces is. All right, so that's what I had to say. Thanks for listening.
So we have time for questions. Oh.
Thanks, Aron, for a very nice review. Just to come back to generalized entropy, if one is going to go beyond one loop, etc., and include the matter contributions, what is the precise statement? Because there isn't even a well-defined notion of a horizon. Is there beyond some kind of semi-classical way of thinking?
Right, so that's an interesting question. Except for the last slide, I'm, of course, trying to stay in at least perturbatively an H-bar setting, but it's a general it's an interesting question. When we would, in full quantum gravity, you could say that because maybe things become more non-local, there's a question to what degree we can genuinely factorize the theory across a given surface, or even define that surface. The one thing I can say, perhaps, is that if entanglement wedge reconstruction is true, then it says that in the very special case where you have this extremal or more generally quantum extremal surface, it's because we know the CFTs factorize. If we believe the quantum gravity is dual to the CFT, then it should be possible to see somehow in the bulk quantum gravity theory that the Hilbert spaces of these two shaded regions also cleanly factorize. So perhaps this is the one case where geometry should factorize in quantum gravity is when it's across an extremal surface. And it would be actually great to see whether this, at what level this maybe starts to come in. One has proposed to me that maybe you start seeing a problem with other surfaces even at the level of perturbatively treating the graviton. I think that's in many ways still an open question.
Thank you.
Are there other questions? Actually, before we go to other questions, can I ask, is our second speaker here? Marcus, any? Okay, could you visit our friends over here to be wired up? Sorry. Okay, other questions? Over here behind?
Hi, you mentioned the JLMS formula is sort of, I think you mentioned it's kind of true at leading order in first sub-leading order in H-bar. Do you know, is there any analogous statement that goes beyond the leading order in H-bar?
There are some statements in this paper by Lukowitz and Dong, where they went to all orders and they defined some actually multiple concepts. There's also an interesting concept if you're extremizing some sort of modular Hamiltonian. I'm not sure I completely understand what they did well enough to give a good answer, but it should be in their paper. But things do become a little hairier. The nice thing about the case where we just stay at leading quantum order is that we can have a clean definition of what we mean. We can think of the quantum states as being defined in quantum field theory on a fixed space-time background, and we can treat the two states, rho and sigma, as living on the same background, which makes it easy to define what we mean by things like the bulk relative entropy and bulk modular Hamiltonian. Actually, for higher orders, you could worry that maybe the concept of the same surface defined in a different state is a sort of fuzzy statement that you need to really understand how diffeomorphisms work at the quantum level, which I think it probably is possible to understand that perturbatively. In my paper with Dan and Shi, we actually, on entanglement wedge reconstruction, we actually tried to make some statements to all orders in H-bar, but I actually feel a little bit guilty about those statements because I'm not entirely certain it makes sense.
Other questions? Can I ask as a follow-up to that, when you talked about the generalized entropy, you started with the expectation value of the area operator, but that's some kind of complicated nonlinear operator. To what extent do we really understand that?
Nonlinear in the sense of nonlinear in the metric.
Yeah.
Yes, so in the concept, mainly, I don't know if we understand it generally. In the case where I was proving the generalized second law, you can argue that the case that's interesting for quantum corrections is when you're perturbing around a classically stationary null surface. Mm-hmm. And in that case, as long as you're dealing with, again, these leading order quantum effects, you can actually justify this expectation value basically from the fact, well, what would go wrong is that the expectation value of A times B is not the same as the expectation value of A times the expectation value of B. But as long as you're just doing linearized quantum corrections, you don't care about that because that's quadratic. Okay. In that sort of regime, you can justify these sorts of statements, but there's probably some interesting renormalization effects having to do with the fact that the area is nonlinear that I don't know if anybody has really carefully thought of. You might want to smear it too, and there's some subtleties there.
Okay.
I agree.
There's Dan.
So this is about this saturation of the QNEC. So I know it's not your work, so maybe I'll put you on.
The saturation of the QNEC, yes.
Yeah, so at least very naively, it seems like the right-hand side of the equation, yeah, there you go, has a H bar on it, and the left-hand side of the equation doesn't. So for example, like in classical hydrodynamics, I might have guessed that the right-hand side was 0 and the left-hand side is not 0. So how am I supposed to think about that?
Right,
from
so
the point of view that is saying that it's
in the
saturated?
situation where this is non-trivial, we're looking at quantum field theory states, and TVV ends up being first order. So TVV for a state with order unity quanta will be of order h bar omega, so it's also of order h bar. So the h bars are actually the same on both sides.
Yeah, but what about in a hydrodynamic state?
Right, so in the hydrodynamic regime,
yeah.
you would probably have this term dominating, I think, and you'd be back to the regular null energy condition.
But you said that it's saturated in interacting theories with d greater than 2, so then it can't be
right.
dominating.
So, but This second derivative involves a sort of delta function of y minus y prime. So presumably the answer to this statement is that the fact that you're taking these two derivatives to be very close to each other, it's important that it's below the scale where the hydrodynamics is valid, and the second derivative that's non-zero that you get in hydrodynamics would somehow be coming from places where y is not exactly equal to y prime. The fact that this statement is saturated seems crazy. I mean, you have a linear thing on one side and a nonlinear thing on the other side. But most of the obvious objections for why it's wrong come from the fact that this is only actually talking about the delta y minus y prime piece.
Okay.
That's why it actually is okay.
Okay, well, let's thank Aron again for his interesting review. And then for our second